Hi everyone, welcome to another Haskell Study Group. I'm your host Ron Batum with Atlanta Functional Programming. Today we're going to be discussing currying, polymorphic functions, and type inference in Haskell, as well as how to assert some type declarations inside your Haskell code so that you can get some of these advantages in your own production level code. Last time when we were talking about functions inside of Haskell, I kind of briefly mentioned and introduced the concept of currying, as well as we introduced currying in a form when we talked about the lambda calculus a few weeks ago, but we never actually talked about exactly what currying means with respect to Haskell itself. To begin with, Haskell has one feature regarding function declarations that I thought I would briefly introduce or briefly mention here. Haskell, you could think of as a pure implementation of the lambda calculus, but and what that means is with respect to functions itself, arguments inside Haskell are nothing more than a basic shorthand for the mapping of a lambda expression as you have seen inside the lambda calculus. To remember what we saw in the lambda calculus, recall that a function in the lambda calculus is defined as, and I'm using the Haskell syntax for anonymous functions for the for ease use. If you guys want to try this out on the REPL, you have an expression that starts out with our notation, our lambda, ahead, if you will, an arrow sign that indicates that we're about to go into the body, all right, and then the body of the expression. Now this is somewhat equivalent to lambda x dot x, okay? This is equivalent to this. When you're dealing with multiple arguments, though, recall that we had this ability to write this shorthand that takes into expressions multiple arguments in the head, and it allows us to write this body, and it's the same as writing xy, x plus y. But if you recall, this is nothing more than being equivalent to lambda x arrow lambda y arrow x plus y. Okay, and here I'm going to go ahead and put parentheses around this for convenience sake. In Haskell, all functions do not have this multiple argument syntax. Instead, what happens is they take the multiple argument syntax and constructs a series of nested functions. And those nested functions look somewhat of this form in the case of two argument functions, and you could think of multiple arguments from there on. And only when all the arguments in the head of each subsequent expression is bound, this final expression is evaluated. This is what Haskell does for all function declarations, and this is what they mean by curried functions by default. Okay, currying is nothing more than this referencing of nesting multiple functions of one argument, all right, and returning them for a function that takes in a single argument. Okay, Haskell itself, bottom line, a function always takes one argument and returns one result. All right. This is and multiple arguments in Haskell, multiple argument functions in Haskell are treated as a series of nested functions, each of which takes in one argument and returns a function that has that first argument bound and the remaining arguments are going to be part of the expression of multiple nested function declarations. Okay. Now we can see this when we actually go and run a simple info on the arrow operator, which, if you recall, the arrow operator is the function type operator that we use to actually define a function. Okay, as you can see here, specifically in the data in the type constructor here, arrow takes in only two arguments. Okay, A represents an argument, the argument being passed into the function that's actually going to be bound to a function inside of the expression, and B is the type that's returned by the expression, by the actual function mapping, right? A and B are here, both are type variables, if you remember our earlier conversations on what that is. We can see a lot of this declarations in many forms, and I think it's good to actually go through some of the existing functions that are available in Haskell to get a better understanding on how one might end up using this out in the wild, and more importantly, how one ends up leveraging this and the other features of Haskell to get more stringent constraints on top of a function. Because as you can see here, in some cases, although not necessarily in this case, A and B are type classes that have no constraints here. Right? There are no type constraints associated with their information. Okay. But it'll become necessary when you're dealing with curried functions that are taking multiple types as to how those type constraints are applied to the type variables in the function declaration. To start off small, I think it's important that we start with exploring the plus operator. Okay. As you can see here, the plus itself is nothing more than, actually I think this is probably better to actually go and look into it. The plus is nothing more than a generic function that takes in two arguments, as you can see here. This is, again, a curried function that takes in two arguments and returns an argument. Okay, so if this is confusing you, this notation here, one thing that I did just to wrap it around my head to see what exactly is resting functions is, you could certainly add in the optional parentheses to understand that num a, let me actually copy this into our buffer here. Example plus type signature. You could certainly go ahead and add the extra set of parentheses, and it is actually equivalent to what we saw earlier. The parentheses are optional, but it is going to take a little bit getting used to see how function application, function evaluation is actually going to address and apply and bind those variables when you are grabbing or evaluating a specific function to a certain number of arguments. Okay. The one thing that is different than here that is particularly of importance is this first thing here, which I briefly mentioned last time, but I think it's important that we dig into what exactly this is in terms of the function declaration and why is it there and what's its role. What num is doing, okay, num, as I've introduced several times, is the numeric type class, okay, on top of our type variables, and it requires certain information to be defined in order for something to be adherent to this numeric type class. Numeric has to be a part of the function declaration when you want to say that this is a type constraints on all instances of the type being evaluated to being constructed and the argument, that is the data argument, being evaluated to a specific function. What I mean by that is at the time of evaluation, when you pass in a particular variable, okay, or a piece of data, okay, a variable in this case could be an immutable variable that you may have defined elsewhere in your Haskell file, versus a function that may be returning an argument and so forth, or even a constant value that you know that you're going to be applying in the case of, say, plus 5, 6. And I'm only using prefix notation to illustrate the function evaluation piece of this, okay? I know that you can certainly use 5 plus 6 for for the infix representation, but this is much easier to explain function evaluation for than infix notation is. What the type class does is at this time is it takes each of these instances, checks up what type is in these constants, then verifies that the type constraint, that particular type that this instance represents, that adheres to the numeric type class, and it has the appropriate operations defined for that instance. Okay, this is how a lot of the evaluation semantics end up working inside of Haskell. Once that is done, and we know that it's adherent, we go to the second argument. We would actually look into the body of the function to see if there's any additional type constraints that may be there. For example, as I mentioned earlier, it might be the case that you might be taking two different type variables, okay, and each type variable might have its own type class constraint on top of, before it can actually be bound to a particular type variable in the function signature. But for the sake of addition, we don't have that worry. We just need to worry about the variables being passed in, and we check to make sure that they're adherent to the type class here for numeric, and then we end up binding them to the appropriate type variable in our function signature. Now, function evaluation, as I mentioned last week, although in application could be is right associative, technically evaluation is left associative. And what that means is when you are using and binding a function, say 5 plus 6, it's going to apply 5 to the first argument, then 6 to the second argument, and then finally, whatever the expression is, will return what we're going to be returning is going to be the same type as the arguments that were passed in here in this case. So obviously in this case, the result is going to be 5 plus 6, which gives us 11. Okay. The boundaries that you are seeing here, specifically this boundary as well as this boundary, as well as even this between each different, they associate what actually is happening between function evaluations. Okay, And when you are reading this, just remember that this definition is plus plus is the colon sorry is defined as the defined as operator. Okay, we're saying that this is taking a function of two arguments with the numeric type class being a constraint on that on those two arguments because they are of the same type, and it's returning a type an instance of the result being adherent to the same numeric type class that was passed in for the arguments. Okay, this is considered to be just a way that you would end up to separate boundaries from type constraint signatures versus from the actual clear definition here. So by providing the type constraints in its own section, you are not actually littering the type signature with any additional information. Instead, what you are clearly expressing here is the lambda calculus version of the function. In this case, we are taking a function of two arguments and returning a value. Another thing that's specific to most of the arithmetic operators that I thought I'd mention here is the fact that since the result type as indicated here by A is adherent to the same type class constraint as its arguments, you might end up getting particular errors if you end up evaluating to a completely different type inside your function. So there are some weird type errors that you're going to end up getting if you're not too familiar with it. Like, for example, if you attempt to add 5 to hello, you're going to end up getting this error saying that you can't actually go and create a data instance on the list of characters. And that means that plus is not defined on on strings. Okay, and more importantly, there's no conversion from a string to a numeric in this particular case. And as a result, you are going to end up getting this error if you do a straight up conversion. Now, for those who might be wondering what happens inside the case where you might have, say, 5 here, what can happen? You're going to still get the same error, but there are functions inside of the prelude that allow you to convert numerics to strings. Unfortunately, right now, we haven't gotten to that part yet, but there are those cases, and in that case, when you are moving from strings to numerics and so forth, you would have to use conversion functions to convert those strings to a particular numeric type before you can go ahead and actually apply and evaluate that value to the appropriate arithmetic operator. All right. This might sound pretty obvious for some functions of folks, but starting out when you're on your Haskell journey, some of it is particularly unusual, especially if you're not coming from another language that does not provide this kind of signature. And there are languages, especially in the ML family, that gives you these kinds of signatures, although I don't know if SML and OCaml give you something similar to type classes. Folks who might know that, I do encourage you to put comments in the YouTube video and let me know, so that way we can all communicate with each other on this. One thing to note about what I wrote here earlier is this function that we are parenthesizing kind of indicates and proves that the arrow operator itself is going to be right associative, although application itself is going to be left associative. So what happens is, in this case, when we are doing partial function application especially, all right, depending upon, and this is particular to all the infix operators, depending upon which side you are binding to the function, you will get a different function results. So, for example, in the case of and this is a brief review of what we've already seen before when we're talking about slicing and partitioning. If you go in and create a partially applied function and you say 5 plus, what this is actually giving you is slightly different than and again, just to make sure that we actually define this correctly, and we apply A to A. Okay. The reason why is since this is a numeric type, we can actually go ahead and use the type class constraints for this. If we apply it this way, what we end up getting as a review is actually add 5 equals lambda x 5 plus x, versus, say, if we do this, we'll get x plus 7. And again, we'll do this by first creating our type signature, and we apply this to plus 7, as so. All right. This difference here is just showing you how things are ultimately going to get bound, but what is actually returned from this partial function application is a new function. This is why this plus here it takes in an argument and it returns a new function. Okay, this is why these parentheses are very, very important. Now, in the case of plus, since it's a commutative operator, meaning A plus B equals B plus A, it doesn't make much difference on how the function applications behind the scenes may give you the final function, because again, at the end of the day, the application will still end up returning and giving you the same result. But it is important to know that this positional argument, when it comes to function application, is useful in particular if you're dealing with functions of different functions that are taking arguments of different types, because then you can apply the types in a different way. And we've seen that with our tuples examples. Now, what I've been showing so far have been applications of functions with two arguments, because that seems to be very simple. That's fairly simple when it comes to actually creating functions. But it might be useful to actually see an argument with a function with 3 arguments. Now, I'm not going to write this. I'm just going to deal with integers right now. And the reason I'm saying just 3 is and you can certainly have more than 3. You can have more than 2 arguments per function. But at the end of the day, just remember, you are just creating nested lambdas here at the end of the day, okay? These are still going to be functions that take in an argument and returns a function. They end up becoming function factories, essentially, all right? For lack of a better term, I'm using the term function factories, but it's a pretty a close analogy to the idea as I understood it. An idea that was fairly simple to do, we could just make a triple function that takes in two integers. Let me call this make integer triple. That takes in three arguments, sorry. And what it does is we're going to go ahead and return a triple of three arguments, okay? So here we just do make integer triple x, y, z equals x, comma, y, comma, z, all right? Now, one of the advantages of this is now, and as we've seen before with partial function application, is since these are nested lambdas and they are curried together, we can go ahead and apply a particular value to one of the arguments in the function and return a function factory of the remaining arguments. Okay, so as an example, we might end up creating, let's say, make triples, make 5. Let's call it triples of 5 for all. And this function is nothing more than a function that takes in two arguments. Now you might be noticing I'm actually writing a lot of signatures here. I'm only showing you the final application of this. Just because this is going to be a partially applied function. Now we're playing with some experimentation here, but this is kind of the same idea. So here we could just say triples of 5, and if we look at it, we end up getting the same, partially applied function. Notice we did not get any error from the remaining functions. Why? Because the fact that although this is an argument of two arguments and then it's replacing it with 3, the fact that it is actually getting a partially applied function makes this type signature here a valid type signature. Okay. Now, if you put in something else and you didn't get that that signature, it's essentially inheriting its original signature from the first one, the make integer. But then it realizes that the first argument's been bound to a particular value, in this case 5, and it's returning you the rest of those arguments. Okay. That's a fairly important, subtle but important point to note, that your type signatures will essentially match whatever applications you're doing prior to the actual definition of the function. Okay, this is happening behind the scenes through the type inferencer, which we'll be discussing in a minute. But it is important to note that that is ultimately the result of having these two things defined. Now, if it had no notion or no way of knowing what the signature of make integer triple is, you will certainly get a type error saying that this function, you may get a type error saying that this function may not apply, return the number of arguments that are passed in, the number of results that are passed in ultimately. Okay, but again, I'm just briefly mentioning that. One more thing also, it could be the case that you are taking these two arguments and you are creating a triple of new arguments here, where the first argument is a combination of these two arguments. But in this case, because we're doing partial function application, that is not what is actually happening. It's checking its signature against the parent signature that it has. To give an example where you could do, take in 2 arguments and return 2 arguments, you could do something stupid like min, max, sum, okay? And integer takes in 2 integers and returns the triple of integers, okay? What this is doing is it's going to give you a triple where the first positional argument is going to be the minimum of 2 integers. The second is going to be the maximum of 2 integers, and finally it's going to be the sum of the 2 integers. And you'll get the same idea here. You get a max, you get a triple, you do min, x, y, max, x, y, and then x plus y. The reason why I put these things in parentheses is because of the fact that otherwise you may end up getting some errors when you're trying to apply this. So now we have this loaded, we can go ahead and do 5 and 6, and we'll end up getting 5, 6, and 11. Right? So you can see here in this example compared to the other ones is the result type itself may not necessarily have any relationship with the arguments being passed into the function, but given the fact that it ends up recognizing that during the evaluation phase, it is the types will line up and everything will go ahead and work out. Now, the type constructors for functions, the types, and the declarations that we've seen thus far, as I mentioned before, are just Lambda applications. You could think of when you are applying a function to multiple arguments, essentially doing beta reduction. This can help you to actually verify your arguments are going to be bound the appropriate way that you are thinking that's happening. You can also use explicit parenthesization the way I was doing it earlier with these functions here. These parentheses are technically optional when it comes to your function declarations, but if that's going to help clear up certain things as you are working through this in the in your early times, then certainly do it. I will, though, ultimately discourage you to use that when you are really starting to write production quality code, just merely because this is standard convention. What we're showing you here with the function declarations, where there aren't any parentheses unless they're necessary, like in the case of representing a tuple. Okay, there's no parentheses in the actual function returning. So, but if this helps you to understand what's ultimately happening, then certainly I won't discourage you from not trying this out, because this is functionally equivalent. It's just that it's not a generally encouraged style to actually do that, because that does some, especially if you start doing 4 or 5 parameters, that does it makes things a little bit convoluted. Although, just as a side note, if you are writing a function of more than 5 parameters, and you're writing it as a curried function like that, you may want to rethink about your type signatures and maybe consider creating a composite type so that it doesn't actually convolute the function type signature itself. Just a heads up on that. Now, explicit parenthesization, okay, such as, let's take another example of a different operator. Let's say we are going to use map an operator. Yeah, here we go. Now, in this kind of function, you notice that there is an explicit parenthesization important for the argument that's being passed in to indicate that this is not necessarily a function that's taking in 2 arguments, but the first argument inside this is a function. Okay, This is where explicit parenthesization becomes very, very useful, okay? Other than the one that I just showed you here, where the result type or even the input type may be a triple or some composite data type. This is another case where you want to use explicit parenthesization because of the fact that you want to be able to know that in the type signature, if your first argument or your argument, wherever your positional argument is, whether or not it's taking a function. Okay. After that, you can see that the parenthesization rules in terms of actually returning functions and stuff still apply here, so they're optional. So in this case, we're seeing that map, which is our standard map function, is taking in a function and then taking in a list and applying the function to the list, returning potentially a list of different types. Okay, this is why A and B here are not the same. In this case, especially, you can see that B is essentially mapping to the B that's inside the function, because that's what we're doing. We're applying the function to each argument in the list, and we are actually going to go in and return it. Now we could see this if we just simply take an example, like let's say we want to double every number in a list. You could take in times 2, takes plus 5, and then we can end up getting the first 5 evens. This is kind of where it becomes useful. The other thing to note is this function being here like this is indicating a somewhat like an order of evaluation. All right, it is explicitly asking that the inner parentheses gets evaluated first before it goes and returns and creates these functions. All right. This idea that we're seeing here gives us this nice little ability to like write functions like say double list that takes in map times 2. We end up now we can actually go in and apply things like that. All right. Remember, the result types, the final set of parentheses is what's evaluated first because of the right associativity of the function type operator. But evaluation, that is what is being bound to the function, is going to be left associative. I know I've been repeating this throughout this entire broadcast, but I know it's going to take a little getting used to understand what this means, okay? And it's really related to it, and it's really important to talk about it, especially when you are learning how arguments are being evaluated when a particular function is being called. All right. Now, the other thing to note is to be aware of is because because Haskell itself is lazily evaluated, even if we write something like this, it may not end up evaluating the rules at all. It might just keep it as part of an execution plan until such a point where you actually do need the actual computation to be executed, and then the rules that we were talking about earlier will get applied. All right. The real power of currying, as you may have seen from the examples that I've been showing thus far, has really been partial application. Because Haskell allows you to use because Haskell functions are curried by default, you have this ability to actually build generic functions and then reconstruct those functions that you need from other functions that have already been predefined with the appropriate variables bound to some values. Okay, we've seen this already in several examples, such as double list, triple of 5, min max sum. Like triple of 5 is where you are seeing that we're using partial function application. Double list is another one. This is just taking a list and then returning a list of type B, and we've seen double list is nothing more than map of times 2. Okay. And we can even further restrict it here, saying that these guys are integers because we are dealing with functions of different types. But this further restriction is not necessary. You could have just simply done this and said, and allowed, let's see, num a equals a of a, and this works too as well. Okay, we're using a generic type variable, but we're adding a type constraint here. I'm going to keep it, since we haven't really talked about, okay. Since we haven't really talked about type classes in real too much detail, I'm not going to put too many type classes in our examples, but I just want you to know that that's another way of actually doing the same sort of constraint that I was showing earlier. But this partial application is really, really important to really learn, because of the fact that once you really understand that what partial application buys you, you will a lot of times will write generic functions, and at the end recognize that you could simply constrain them for particular types if and when necessary, and you take the full power of partial application to design your pipelines. But that is a series of transformations that you are actually going to go and apply to a particular data type. This actually illustrates the kind of tacit style that most people who are in Haskell end up writing, and that is a point-free style in Haskell. And so far, we've actually done many kinds of this because of the lazy evaluation here. Although we've defined double list already, we haven't actually evaluated it until we've actually applied it to a list here, to a data item, that allow all the variables to be bound and the expression to be evaluated. Now, although functions are curried by default, you could actually uncurry them, but we need to understand, what do you mean, what does uncurrying mean in the Haskell world? What that usually means is, in Haskell, given a function that takes in multiple arguments, okay, let's call this f, okay, and let's go ahead and say that this is some sort of generic function that's applied. We're not going to deal with any specific types, okay, right now. What uncurrying means is we're going to transform this function, okay, and we're going to create a new function that ultimately takes the number of arguments here and converts them into a tuple, okay, and then this is your uncurried version. It's now a tuple of multiple arguments that you'll now apply to with some sort of type constraint, okay. An example of this is if you've uncurried the plus operator, you might end up getting a different, you'll get a different function that'll take in 2 arguments as a tuple and return an argument of the same type, okay. A lot of older languages, older functional languages, pre-Haskell, and I'm going to say this, really is just functional languages that are technically eagerly evaluated tend to end up defaulting to using product types to express multiple argument functions. And so OCaml is one that would ultimately do something like this. So uncurry a function, I think that there was a function called uncurry. All right. And if we do an info on this uncurry function in Haskell, it will literally take in a function of multiple arguments, in this case, 2 arguments and return a third type, and it'll convert it into that function that takes in a tuple and returns a type. We can apply this actually to the plus operator, and you'll end up seeing that it's now a function that takes in a tuple and returns the sum of those elements that are in that tuple. To curry an uncurried function, the nice thing about what you can do is, in some cases, you might take a uncurried function to be passed in for some data transformations and then want to curry it in appropriate cases. You could do that inside Haskell by using the curried function, which will essentially undo everything that the uncurry function does. So if you do curry of uncurry, you'll end up getting the same original function that was generated. So in this case, our plus operator signature, and you could see this if you just simply do type plus, and you can verify that. Okay, that the signatures are exactly the same, although the type variables maybe end up being different. Okay. Currying and uncurrying is used a lot, by the way. These curried functions that we had, mainly because of the fact that, like I said, because it's curried by default, partial function application oftentimes ends up becoming the basis for designing generic functions, and in certain cases binding arguments to particular values when appropriate. So that way, your special edge case you need to account for, you then design a function around that. But even those cases, you might still use the partially applied functions as a basis to designing your higher level algorithms. Does that make sense for folks? I'm going to briefly stop here for questions. So if there are questions, please post them to the chat in the stream, and I will answer them accordingly. All right. So, the last thing I want to talk about with respect to currying is something that we mentioned, I mentioned in a previous episode, that is this term called sectioning that is used when you're partially applying functions to infix operators. To review, we've seen this already in some examples as I've been using sectioning already with doubles, their double list example. But to start off, I'm going to go ahead and use a different example. Sectioning itself, if you recall, was a special syntax that allows you to apply, to decide for a given infix operator whether or not you are partially applying the operator to the first argument or the second argument. Okay, and depending upon which argument that you are applying to, you might end up getting a different function family. Okay, now with commutative operators, which is what I've been using so far, like plus, times, and so forth, applying the argument order does not matter. Okay, applying the argument order does not matter. Create functions that ultimately evaluate the same result. Okay, we've seen this with if we use add 3 to being plus 3 here versus 3 add, which is equal to 3 plus. All right, oops, sorry, I have to go and change that because I forgot that we can't use numeric here. We'll call this triple. We'll say 3 add Okay. And let me go ahead and do add 3 here this way so we know what the difference is. Okay. Now we know both of these ultimately, if we look at the type signatures, they are both the same type signature. Okay. They are both a numeric that takes in a value, returns a value. Add 3, but they are free add is a very different function in terms of what it's actually valuing to. So it's taking in an argument, okay? And again, I'm just going to define it mathematically. It's just a lambda expression that goes ahead and does 3 plus x versus add 3, which is x plus 3. The one thing to note is although, because addition itself is a commutative operator, these two are ultimately going to give you the same result. So you may never know whether or not, because of the commutativity, whether or not you're doing 3 plus x versus x plus 3, unless the author of your API does what I did here, which is indicating where the application is being applied in the name of the function. Okay. Where this becomes very, very important, as you may recall, is when we're dealing with non-commutative operators. An example of this is the exponential operator. Okay, the exponential operator gives you essentially an infix operator to which that if you apply the function, partially apply the function and section it on the left hand on the first argument, you'll get a completely different function family than if you partially apply the function to the second argument. So let's illustrate this with an example. So again, to show you what the type of the infix operator is just taking an integral type and a numeric, and then it goes ahead and creates a function of those two types. Notice in this example here, the type constraint signature is written as a list. This is how you would normally write your type signatures with a type constraint on multiple arguments. Okay, although this guy is a tuple, all right, the actual function signature does not need to be an uncurried function. Okay, it can be a curried function. This is just allowing the type inferencer to go in and check all those types in one shot rather than actually taking each particular type constraint and applying it to all the variables in a particular function. This tuple has its advantages in the type constraint section. So we know now that we're taking an integral type and we're taking a numerical type, and we've already seen this before, but I'll go ahead and redefine this as our illustration. We could certainly create a function called powers of 2. Okay, and this guy is obviously, has the name suggests, giving you the powers of 2. All right, that's 2 to the x. Okay, so our powers of 2 now function is basically lambda x 2 to the x. All right. Whereas if we apply partially apply 2 to the right-hand side, and this is a mistake that a lot of beginner Haskellers do when they're learning sectioning, you've created a completely different function. You've actually created the quadratic function, okay? So you are creating your type signature, if we're creating that, is essentially, let's say, squares, okay? And what square is doing is it's nothing more than applying this to the right-hand side. This guy is a different function itself. It's creating essentially lambda x equals x squared. All right. Not knowing the commutativity of the operator that you're dealing with will make learning how to use sectioning to your advantage very, very difficult. So one suggestion is to be aware of the operators that you're building. All right. A lot of the arithmetic operators, they are very well defined. You could figure out from their signature and from their application as to the type and function families that will end up being created from them. But you need to be aware of this specific nuance when you're using sectioning so that you don't accidentally name a particular function to be a function family that actually it doesn't actually represent. All right. So don't worry if a lot of this stuff about partial application doesn't doesn't register immediately. If you do enough practice, you'll get a very solid intuition of it, and it'll become second nature because you will end up using it a lot. So let's talk about polymorphism. Now, to begin with, we need to first talk about what a polymorphic type is and what is a monomorphic type and what polymorphic type variables gives us, and we can work our way up into what Haskell supports. All right, a monomorphic type. All right, to begin with. Okay, so polymorphism. We're going to start with monomorphisms. Okay. These types are essentially made of one specific form. What that means, there's a clear definition of what the representation is and what operations can be applied to this particular type family. And if this type ends up being in any type signature, we know that there's only one way that it's going to be represented, is to actually apply that function to those types, right? Polymorphic types, on the other hand, are an extension of this guide, but it's really creating essentially flexibility and allowing us to create expressions that ultimately return results. So we can implement and create expressions. And by expressions, I mean like lambda expressions that essentially take in arguments of one type and return results of a different type. And here's the kicker. You are doing this without actually having to write special methods for each specific specialization. Okay, so you're using the same expression for each different type. You're using the same expression to represent the computation of a type family, all right, by using a polymorphic type, okay? That's what a polymorphic type is, okay? The idea is you are writing the computation, what you are transforming on a type family. That is a series of types that adopted or all sort of have a definition of a certain characteristics that allows them to be transformed the same exact way. An example of this is actually something that we've been seeing this entire time, which is the numeric type. Technically, the numeric type is a type class, is representing a polymorphic type, because when we're talking about numerics, we may be talking about floating points, we may be talking about fixed points, we may be talking about fixed precision, we may be talking about scientific representations, rationals, reals, straight-up integral types, although with integral types you have further restrictions if you wanted to talk about fixed point numbers versus, fixed nums versus big nums that have no overflow, that are of arbitrary size. The type class itself doesn't actually restrict your transformations on those types, but by having that type class, you are representing a family of types that all can be transformed in a very similar fashion, which means any algorithm that can take in a numeric type can take in floats, reals, integers, numerics, and it does the right thing. It will actually go ahead and efficiently do the appropriate thing to actually generate those things, those appropriate expressions. And it's the same exact expression. It reduces the amount of code to represent a series of types, and you'll be able to better test it for different types if and when appropriate. Okay. All numerical functions available in Haskell, as far as I know, are polymorphic because of the numeric type class and its definition and what it represents. Okay. When we talk about polymorphism in Haskell specifically, though, all right, we may be talking about one of three families of polymorphism. Okay. And there are three types of polymorphism in Haskell. Okay. The first one is concrete polymorphism. Okay. I'll mention the definition for each of these as we go around. Let me just first document what the three types are for right now. The second one is parametric polymorphism. Okay. And the third one is constrained polymorphism. Okay. You technically also have ad hoc polymorphism in Haskell, but ad hoc polymorphism is technically implemented using type classes. Okay. And the reason why I wouldn't consider it necessarily ad hoc just merely because ad hoc, when we're thinking about ad hoc polymorphism, oftentimes we are thinking of them in terms of how they're implemented in existing languages like C or C++, which is using some sort of overloaded functions syntax where the function signature indicates the overloaded version. So you can have the same function name that's taking different arguments, and internally what happens is when you look at the compiled code, especially the assembly, how the name mangling occurs at the assembly level determines which function call you're actually going to be calling, and that's what's actually being used by the compiler to verify things like the types are being passed into the appropriate function, the types are adhering to a certain top level set of concrete types, and so forth. Haskell, with its type classes, its approach to ad hoc polymorphism is slightly different, and I don't think it fits the analogy that those other languages provide in terms of ad hoc polymorphism. I'm briefly mentioning it here just because most people, when they think of ad hoc polymorphism, they're thinking of those older languages and how they implement polymorphism for function overloading. So constrained polymorphism actually in Haskell, I was kind of lying a little bit here, is a form of ad hoc polymorphism. Okay. And it is something that you've encountered a lot so far when you are dealing with Haskell. Okay. Most of the examples that we've seen because of the type classes are essentially using this type of polymorphism. Okay. But parametric polymorphism, okay, itself is much broader. It's a level above. It's more general than ad hoc polymorphism. What it's talking about is how do we generate a function expression that can refer to one or more type parameters, all right, type variables, that themselves are fully polymorphic, okay? An example of this is technically, the example that we have up here, which is our function of, our generic function of 2 arguments. Let me just bring it down here. And let's go ahead and, actually, let me just go ahead and do this. Bring this down and redefine it here, because we don't necessarily need the uncurried version right now. Okay, this is our function that takes in 2 parameters, okay? This is a form of parametric polymorphism because it is referring to your type variables, or your parameters, and each of them represent a fully polymorphic type, okay? When it's unconstrained by our type class constraint, as we saw in other functions, we don't necessarily know what the type is, but what we do know is that it could be anything. Okay. When you restrict it with the type class constraint, as in the form of constrained polymorphism, using a type class, you are actually adding and actually reducing the search space and reducing the type verification that's going to be put upon this this type, and additional type checking, and this is more important, is going to be applied to the type instances prior to actual evaluation. Okay, that's where constrained polymorphism has a slight difference. Might be even end up giving you far more efficient code in many cases than parametric polymorphism. But there are certain operations where parametric polymorphism in these kinds of generic type variables come into play and become very, very useful. All right. You can certainly start with a parametric function like this that we've just I'm showing you here, and then start adding your type constraints if it ends up turning out to be the case that you require more constraints on top of the types prior to doing it. But by doing so, just know that you're no longer in the parametric space, you are in the constraint space in terms of what your polymorphic function is and what it represents. This nomenclature, although is further categorizing polymorphic functions, which is slightly different than what most people are familiar with or comfortable with, it becomes important when you are reading type signatures so you know what you're dealing with, all right? Our canonical example of a parametric polymorphic type, is actually something that we've been dealing with even in the lambda calculus. Although this example that I gave you is just some generic type, I didn't actually implement anything, but we've already encountered something that is a purely parametric polymorphic type function, and that is the identity operator, right? It is literally taking anything and returning anything. Notice there is no type information on what constraints need to be passed in order for this type return itself. All right. This means that this generic function, this purely parametric polymorphic function, can work on anything. It can work on integers. It can work on lists of strings. It can work on even a simple, let's say, let's say that we have a successor function, okay, x plus 1, okay, so success 1. We know that we can also apply this to functions too as well, so if we do id success 1 to 2, we know that this is going to return success 2 and then return, which is evaluated to 3, all right? It can work on any type that's provided on it. This parametric polymorphic definition has the same exact expression for any of the type variables that are being passed into it. And because there aren't any restrictions on those type class into it, your expression can take in any type and then be evaluated as according as you think. Another example that you might see this in is the I think yeah. So another example of this, although this isn't technically a purely parametric polymorphic type, but it's you could see it also in concatenation. The reason why I say that this isn't technically a purely parametric polymorphic type is because technically the fact that we're using the list syntax here to represent a list of values, which can be any value. All right, this can work on any. And the reason why I say it looks like it's a form of a parametric polymorphic type because you can essentially apply this to lists of integers. You can also apply this to a list of strings. And it doesn't really matter. The actual concatenation operator is still working the same as it would. The reason why I didn't say this exactly is because technically I think even in this notation, list is considered to be a type class, although it's not actually defined as such, which is kind of weird. But I could be wrong. This might be just a purely parametric polymorphic type. The reason I'm just mentioning it for discussion is because, again, this has the same sort of behavior semantics as we saw earlier with the identity operator, because A, again, can be any type. There's no restrictions on what the internal type that the list holds. There's no type class constraints on top of it, so you can essentially apply anything to it. So this is another version of the idea. Okay. Types don't necessarily need to be concrete in terms of being applied to these generic functions. They can also be applied to any type class too as well. But since we haven't actually talked about type classes too much in detail, I'm just going to briefly mention it here and then leave it at that. In terms of the type variable, I think you can tell that these are generic enough, and type variables can be any type. It can be a possible set of types, and unless you put a type class constraint on top of these type variables, it's just going to assume that anything can be thrown into your function. So be aware of that when you're writing your functions, if you're writing generic functions, just because that is something to be. That's a common mistake with that you end up using a generic type variable inside your function signature, and not realizing that you need to add a specific set of types, and you're getting particular type errors at the REPL. Until we start going and talking about type classes, my suggestion is to just be careful on using or trying to attempt to write generic parametric polymorphic functions. Once we address the issues with using ad hoc polymorphism with type classes, you'll know and you'll start getting an intuition as to when you should use it, when it is appropriate to use ad hoc or constrained polymorphism versus parametric polymorphism versus, say, concrete polymorphism, which we're going to be talking about in a minute here. Now, I mentioned concrete polymorphism because we're really talking about our types that are already implementing various one or more type classes. Because of the additive nature, because of how type classes can be applied to a particular set of concrete types, it can end up creating essentially a type hierarchy, an implicit type hierarchy over the way you've applied the type classes. So, for example, we know an int, which is a fixed num, is an int. Okay. hold on a second. There we go. We know, based on our discussion about integer types, which I think I have here in this definition somewhere. Here. Okay. We know that this int is going to have a certain set of operations when you're talking about fixed nums, because it implements and it makes use of methods that are in the numeric type class, and since it's an integer, the integral type class. But num itself, the numeric type class, is a superclass, if we can think of it, has that of other type classes, right? And that means that as long as those other operations are defined, you can certainly apply those operations to a normal int, okay? So concrete types, because they are implementing one or more type classes, they have some flexibility in terms of mix-ins, in terms of what operations are defined on the top-level type classes and what they're inheriting from. That said, you might end up seeing some potential expense and weird behavior if you end up using different type classes that are disjoint. They aren't actually applied to each other, just merely because, as we saw before, it's going to attempt to convert one type class to another type class, or one concrete type to another concrete type through the type class, and you end up having an error issue that we saw earlier in the case of trying to add a numeric to, say, a string. Okay. Specifically that instance, it's going to attempt to do a conversion that may not be there. Okay. So the general rule of thumb, based on what we've seen here, is, okay, that I think is important to be aware of, is general rules of thumb when it comes to types. Is one, if a type variable has zero constraints, it's unconstrained, okay? That means the transformations that it can be involved in are very little, all right? And that's merely because, again, since it can be anything, you can't guess. You're going with the lowest common denominator of that type, of that any type, okay? So you could probably do something like what we saw before. If they're all of the same type, you could probably construct a new collection, which is a collection of all the types that you've already passed into it. You could, create generic tuples. You could type construct a lot of containers with that data information. You can run the identity operator on it, but in terms of actual transformations, in terms of actually implementing algorithms that actually do it, there are, in a lot of cases, without adding some additional information, there isn't much you can do, all right? And that's merely because it can perform. Transformations that can be performed on the instance of the type is limited due to not knowing what operations it supports. Due to a generic type variable. Actually, this is a better way of saying a generic type variable having few methods to specialize on, right? Operate on. Now, if we apply this to a type classes, okay, a type class, if a type variable is constrained on one or more type classes, and again, we'll be talking more about type classes in next week. it means there are methods that it defines, that the type defines, that allows certain types of transformations to be performed on instances on it. To be performed on instances of that type. So things like, in terms of numeric types, we've talked about, say, we can add on it, subtract, we could do all the arithmetic operations, you can you can apply the exponential operator on it. There's a lot of things that the numeric and integral type classes define on it, so we can just go ahead and verify that it is it can do that. All right. The third thing is if we're talking about a concrete type, all right, if a type variable is actually an actual concrete type, you're losing a lot of the expression loses a lot of flexibility on what values it can operate on what values it can operate on. Okay, like for example, if you're using one of the functions that I created earlier, like our make triple, since we've restricted this on integers, this function will not work on strings. This function will not work on floating points. It cannot work on any, because we've restricted the concrete types in type signature, saying that we know that this is going to be restricted on. Okay, we lose some flexibility there. But since it can have one or more type classes inherited to it, okay, since a given concrete type can have can inherit from inherit. I'm going to be very I'm loosely using inherit here, but because a type class, you are essentially writing an instance of it and defining operations against that interface. But for lack of a better term, I'm using the term inherit. Our type classes. You might have some extension methods from the type classes defined on it that might be useful. All right, this is kind of what I'm kind of getting at here. All right, it can gain some extension methods. And potentially more methods applied on the appropriate type classes. This is kind of what you're looking at in terms of rules, in terms of types available inside of the Haskell system and Haskell programming language. I think understanding this and how type constraints apply from the most generic, which is what we saw, through constraint polymorphism to parametric polymorphism and using concrete types, understanding how that hierarchy works will end up allowing you to write fairly flexible type safe code that is fully that can be applied to one or more types. All right. A function itself, the function that we saw before, so let me see if I can pull this up again. Yeah, let's bring back the infix operator. On exponential, all right? 1 second. Now this function signature is an example of a polymorphic function, all right? The type signature itself can represent more than particularly one type, all right? There are a lot of subtypes around here of numeric and integral type classes that can be particularly useful to be aware of, all right? in order for this to be fully polymorphic, you're going to have to end up doing what we see earlier with the concatenation operator. You would have to somehow declare these type variables in terms of generic type variables instead of constraining them, right, by a type class. But in general, a polymorphic function, as we've seen here, has variables, type variables associated with it that can be represented with one or more types. These type variables are usually lowercase. When you're starting out with and you don't specify any types and you have unconstrained types, just to sum up what we've uncovered this time so far, unconstrained type variables are encouraging a parametric polymorphic type function to be created, whereas type classes end up creating more of a constrained polymorphic function that allows you to constrain the type of subtypes that end up being applied, values that end up being candidates to be applied by this particular function. All right. By having parametric polymorphism in the language, we end up having a property about the parametricity of a particular function. Okay, that I think it's important to understand what that means. And it's mostly related to how a function behaves with respect to the types of its arguments. The basic idea of parametricity is basically that the behavior cannot change for a function evaluation if you're dealing with generic types, type variables, regardless of what type is being passed in. Okay, and what that means is this expression, all right, whatever this is defined on, whether it be in the exponential operator case or in the case of concatenation, it should not be dependent, the implementation should not be dependent upon what type variable is being passed in terms of its behavior, in terms of what it returns. You might have certain different implementations on the type of container that's ultimately being returned, but that should be indicated in the type signature as well, all right? If it's not indicated in the type signature and you end up changing its behavior, you are violating parametric polymorphism, and you'll end up getting some type errors in Haskell. Just be aware of this. This is something I haven't encountered yet, just because I tend to follow the rules of thumbs here, just through my Haskell learning experience. But it is something to be aware of, that there are rules in terms of how parametricity is working in the Haskell programming language. Okay, so the final topic that we're going to be discussing is inferencing and how the type inferencer works in Haskell. But before I start on that, are there questions that people might have on what we've covered so far regarding polymorphic functions? Okay. I know so far there's been a lot of talking, not as much code for examples, but a lot of the earlier parts of understanding Haskell is related to some nomenclature to begin our discussion and building it up. We'll start going into more pragmatic issues and practical issues as we start moving more out of the realm of terminologies and terminological problems. But it's important to understand these terms, because honestly, when you are writing your Haskell code, and if you're writing functional code in general, knowing what these terms are much like learning the design patterns in the language, because it allows you to communicate your design to other folks, especially as you are building up your systems. So understanding and being able to communicate that through that nomenclature will help minimize confusion between folks, especially folks coming in from other languages, because there's a clear definition for a lot of these bits and pieces. All right, and that brings us to a feature in Haskell, and honestly, it's been a feature that's being adopted in a lot of other languages too. And that is the Hindley-Milner, the type inferencing algorithm that's being implemented in Haskell. Okay, first off, to begin with, I'm just going to say this up front. Haskell does not obligate you to actually assert a specific type for every expression. Okay, we've seen this in our examples here. Now, although there are warnings when you are defining functions like this, all right. Multiple declarations add. Let's go and instead of constantly using add, let's say we use product, right? A times B, right? We can see that Haskell does not obligate us to actually write a type, but it will throw up a couple of errors in the a warning saying that there isn't any type signatures associated with a particular type, but it infers a particular type based on the operator that's being provided into this. Okay. Type inference itself is an algorithm. Right? There isn't actually. It's not actually a phrase. Right? It is an algorithm that implements the ability based on the type of expressions and the values that those expressions can operate on. It can infer what types of values ultimately should be passed into the function in order for the ultimate signature that it determined to be conformant. All right. So in this example here, this warning, it recognizes the fact that this algorithm uses the star operator, the multiplication operator, and it can look up that operator, recognizes that, oh, wait a second, this is taking in two arguments, both of which need to adhere to the numeric type class. So this must have also a numeric type class constraint as well. And it was able to infer those types to actually determine whether or not what operations are being, ultimately being passed in. The inference engine that Haskell is built on is a variation of and it's an extended version of the Hindley-Milner type system. Although the Hindley-Milner, it's also some books are also saying that it's Damas is Hindley-Milner as well. It goes by other names too as well. But this type system is often used in a lot of ML variants. So I'm talking about SML, Objective Camel, F# to an extent, although F# also adopted not just Hindley-Milner, but it also actually moved towards doing whatever the type system that C# is built on, so that it could leverage the .NET class libraries. But the basic idea of the type system is from this family, right? The way Haskell actually infers the type is it takes the most generally applicable type that is still correct for the operator that's being performed on for the values. And that generally applicable type, which could be polymorphic, all right? It's a generally applicable polymorphic type. It infers it by first starting with the values that are being passed in as arguments, figuring out what types they are, and working its way up into determining in the parse tree what those ultimate types are. All right. When you're as you learn more and more Haskell code, as you read more and more Haskell code, this inferencing algorithm will become a key tool to how you're figuring out new code. All right. So you'll no longer look at what the code is doing to determine if the types are accurate or not. Instead, you're looking at the type signatures to make sure that they all map out. But for those of you who might be coming to the conclusion, well, that means you don't need to know what's going on in some cases. That's not entirely true. Some folks, for some reason, uses the same name to implement an algorithm that is entirely different than what the name is actually explicitly intending that it's supposed to do. So, although this will at least verify that your program can compile, it may not verify or may not guarantee that your program is going to be working as intended. So, when you're working with open source code, especially, I encourage you to not only just look at the type signatures and figuring out whether new code is going to is going to adhere and fix and actually extend the system the way you were intending it to. You still need to write tests and actually do proper good software engineering practice in order to engineer software that actually is not only type safe, which Haskell gives you for free because of the features of its type system, but also implements the requirements that a particular customer is asking you to do. All right. I know I shouldn't be having to even mention that to most folks, but it is something that is commonly argued amongst a lot of fanboys on a lot of programming languages in general, not Haskell only, saying that if you can compile it and all the types match up, then you're good to go. There's a highly likelihood that everything is working. That again is not necessarily true. You still need to follow standard best software engineering practice. All right. An example of how to learn about the type inferencing in Haskell is to work through a conversation of a debugging session, how you might end up using the type inferencer, right? Remember, debugging types and type signatures is essentially having a good interaction with the REPL and learning how the REPL works, okay? So let's start with a simple example by writing our own identity function, okay? My ID x equals x, all right? We go look at my ID, you will look that it takes in any type variable p and returns a p. You will see that, again, this will work for any variable that we defined and so forth, okay? Now, remember, since Haskell defines all these as lambda expressions, okay, we are essentially doing beta reduction here. Specifically due to the folks that are looking at this, just a heads up, although this is using a different type variable, this is identical to my ID colon a arrow a, because remember of alpha equivalence. Alpha equivalence allows you to use any type variable name and doesn't make any difference at all. All right. We can certainly use this to infer the type of the algorithm, okay? This is particularly useful in the REPL because you don't want to necessarily always define your type signatures when you're in the REPL, okay? You want to necessarily use what the inferencer can do to help you interact with it. And when you figure out what the signature should be, you can certainly enforce that by copying it over into your file of sort. So for example, let's say that we want to create a greeting function that takes in something, some sort of greeting, and then it will, we'll call it greet as a variable, and we'll, concatenate the two variables together, okay? So here, if we look at the actual type, right, it's going to infer the type based on what the concatenation operator allows them to do, okay? But this is not something that we want because of the fact that, wait a second, this is telling us that it is a generic function that can concatenate two lists. That's not too useful for a function that should really be returning a string, right? So one way of actually fixing this is x plus, I think you can apply
think you can apply a type class to this guy by doing, shoot, what is it? What's the notation for this definition? I think I could do something like this. This probably is going to be an error. Yeah, it is. What is the way to actually do this? This is going to be... Let's go and create a simpler function of this, and then we can figure out how to apply a type constraints on it later on once we've learned more about type classes. If we actually go in and say greet Bob, all right, we can go and apply this to Bob. You'll see that the same concatenation operator, but now it's taking in a list of strings. Now that it's taking a string, which is an alias to a list of characters, you'll see that greet Bob is definitely different than greet, in that it recognizes that it needs to take in greet. It needs to take in a string, and it will return in a concatenation of two strings. Why? Because it recognized that string is actually one of the concrete values here, and based on that, it recognized that, okay, because this is a string, this must be a string in order for the type signature ++, which you saw before as being a list of anything and another list of anything, concatenation of the two. Since this value restricts it to being characters, everything else will end up getting inferred as being characters. All right. So this ends up allowing us to then use greet Bob, and allows us to actually end up inferring what those type signatures are. All right. Now, we've ended up taking a polymorphic type signature and creating a concrete version of the type signature by just simply providing a value that matches the constraints of this guy, the ++ operator. That is, it is a list, but it also further constrains the signature in that it recognizes that this is not just any list, this is a list of characters. All right. So then what it does is it takes this template, okay, and applies character to each remaining instance of the generic type variable A, and that's what gives us this final signature here that takes in the list and returns the list, right? Because this is you should think of this as being a partially applied function, essentially. All right. This is different than our greet because the greet, the generic greet, has no type information. It doesn't know what X or Y is being passed in, so it can't figure out what is ultimately the right signature in order to actually infer it. All right, so it used the most generic signature that applies to it. Okay. The one thing to note here is when you're typing this versus actually providing a function name, you're not going to get any difference in terms of what happens at the REPL, at least when it comes to editing Haskell code in files versus editing it in the REPL. But you will get these warnings because the general rule of thumb is for Haskell code running in that is in a file, it is normally encouraged that the type signatures are available but it's not required. That's why you get warnings instead of warning has errors. All right, you could certainly turn this guy on in GHC as you see this $W missing signatures. You can actually enforce that your you can actually enforce the type signature to being always available by using that -W missing signatures. It's just I don't know whether or not, in what cases, it might be useful to do that. That might be useful, especially when you're compiling larger scale systems, to have the type signatures being always available. But in general, as we see here, you don't need to provide the signature versus actually providing your own signature here. You could do both, and both of this will end up being the same thing. A. So here you can see that product A 5 times 6 will give us, oops, that's right, I forgot. I should do my product here. Here we go. My product 30 versus prod 5, 6, which is 30. All right, but if we look at the type signatures of these guys, one is inferred, the other is explicit, and they look exactly the same. All right. This should tell you something about the signatures. It can infer it in a lot of cases, but it is usually something that you might want to keep. Use the type classes. All right. Some reference material I've read, it says is when you're using type classes, especially in the type signature, it makes it might be clearer to assert the type classes in the type signature. Otherwise, you might end up getting undefined behavior, like it throws an error saying that it isn't clear as to which type you meant when you are actually applying a function to certain values. All right, just to be aware of that. Now, to assert type declarations, we've already kind of talked about this. This is just simply the application of what we were doing before, which is applying the signature itself. Most of the time, rather than depending upon type inference, which you're using in the REPL, when you are defining the signatures in the file, it is generally recommended that you add in the type signatures because it's providing you essentially quote-unquote guidance and helps the compiler to actually optimize your code. So, like I said, for folks who are reading this warning message that's on my machine here, it might be useful to actually turn on -w missing signatures when you're compiling your code. I don't know necessarily how to make that a requirement when we're using the editor. That is something I'm looking into, but in general, that is something that you might want to be aware of, just so that you can force yourself to get into the habit of, when you're especially editing Haskell programs and they're becoming larger, your type signatures are available at your disposal to document how types should align, right? So that's it for today. I don't have much other things to mention here. There are a couple of examples that I want to end this discussion regarding types, and especially asserting types, that you may want to be aware of. One is in the case of using types in code, especially when you're talking about using where clauses. An example of this is let's say that we are creating a triple function, okay? Let's go back to my double, just because I like my double function. We're taking x, and we say double it, and we're using where, okay, and we're actually providing the function signature internally. In this particular case, you don't necessarily, it will not throw an error because of the fact that you have the lexically scoped variable to be type defined. All right. Really? That's interesting. It looks like newer versions of Haskell has this requirement that you need to actually define it here. Doesn't seem to be inferring the type here, although it recognizes that it's there. So this has the same problem as what we were seeing earlier. If we do this, let's see what happens here. No errors. Okay, interesting. So although you can use type signatures inside your where clauses as well as your let expressions, just be warned that if it's a top level binding, if it's a top level function inside of a file, it will not infer that type at the top level, and it'll give you a warning. I mean, it will infer it, but it will not actually what's it? It will not enforce it. It will infer it, but it will throw a warning when you are looking at the actual signatures. Additionally, and this is something that I think is important to be recognized, and that is we've seen an example where we can do, say, x equals 5 plus 6. But if we try to restrict constraints tx, we can actually restrict the types in the integer, in the expression by just simply using the : operator. So in this case, if we look at x, we can see that it's being inferred as an integer because we further constrain the integer. Now, this is another way of declaring types and asserting types inside your functions. Especially, you could start, for example, here in our dummy one here. We could say that although we want to take any numeric type and return a numeric type, we can actually say we want to restrict this to be in an integer, and this will actually throw this error because we're saying one is a less rigid type variable than what's actually being passed in. You see that there? So knowing when to actually restrict your types and knowing when to not restrict your types is pretty useful. You may want to be aware of that. Okay. Okay. What's the other thing I want to determine? The one thing that where declaring types might become somewhat problematic for folks coming in from other languages is trying to recast a type to a particular type, especially when you're trying to convert it in an expression. Okay. An example of this is, let's say that we want to return our calculation as a string. Okay. So we might do 5 plus 6. All right. And we want to return this as a string. You'll end up getting errors like this because of the conversion operator of converting a like a 2 string is not actually being applied here. It is actually trying to take the string operator and try to convert it first to a numeric instance, and before applying the actual plus operator. All right, and that's that is a invalid thing to deal with, just because you are obviously trying to convert an operation and not a result. So since string doesn't implement specifically this type class, we're going to end up getting this error. To work around that, there are some functions that you can, again, use to convert two strings, and we will see those. Those are specifically functions that end up implementing a specific type class. I think the type class you need to implement is called show, but don't quote me on that right now. But bottom line is don't try to specify, over determine specific types, or try to do very crazy type conversions or typecasting, because you might end up hitting these kinds of weird errors where the type class that it's actually inferring for the operation is different than what you specified. And since what you specified doesn't implement that type class, you'll end up getting this error message saying that I have typed to construct this type class from the type that you've specified, and it doesn't implement this type class, so I can't actually go ahead and complete the operation. Beware. These kinds of weirdness will happen when you're starting to play more and more with types, but it is something that can often happen, and you just need to make sure that you know what operator or what types a particular operator requires, and that will actually tell you the rules on how to potentially further constrain the types, or further relax the types, depending upon the case. All right, that's it. I'm gonna stop here, and I'm gonna pause for any final questions. All right. I'll see you guys next week, man. Thank you so much for joining us. Just to close out, Atlanta Functional Programming is always looking for talks. For folks who are interested in giving talks on functional programming in general, please ping me or reach out to me on either the functionalprogramming.slack channel. I'm also available on the Lisp Discord server as well as Bugram. And I'm usually squatting in the Lisp channel on Functional Programming Slack, on Tech 404. We're available also on Tech 404 in the Functional Programming channel on Tech 404 too. If you guys want to have ideas or proposals, please feel free to, join those servers and, reach out to me. As usual, Atlanta Functional Programming on a weekly basis does not only our Haskell meetup, we also have a Common Lisp meetup that meets every Saturday from 1:30 to 3 Eastern Time. Please look at your appropriate international, time zones and adjust it for your time zone. And I hope to see you either at that or see you next week for our further exploration on Haskell, specifically when we start talking about type classes. So until next week, I'll see you guys later.